We are discussing internal flow in a pipe or in a tube, and we have seen several ways by which the flow then simultaneous heat transfer inside a tube can be expressed. The first thing what we have done is we defined what is known as thermally fully developed flow, and there we have seen that in thermally fully developed flow, though the temperature will be a function of axial position, the shape of the dimensionless temperature profile will not change with the axial position. That is how we have defined what is known as thermally fully developed flow. We also have seen that the heat transfer coefficient remains a constant for a thermally fully developed flow. So, H will not be a function of x. We have applied the concept for the case of flow in a circular tube, laminar flow in a circular tube. Whatever we have discussed so far deals only with laminar flow. We did not introduce turbulence into our discussion so far, which we will do today. We have also seen that the two cases which appear in most of the times is one where the surface heat flux is constant, and the second where the temperature of the tube wall remains a constant. So, it is either a constant surface wall temperature or a constant surface heat flux condition, and the constant surface heat flux condition we have analyzed in the last class. So, we started with the equation of energy, and we have assumed that it is a two dimensional flow. So, we have written the energy equation, and what we saw is that some of the simplifying assumptions that we could do for the case of laminar flow. For example, we have neglected the axial conduction of heat as the fluid moves in the tube. So, it is a radial conduction which is important. So, we solved that equation for the case of constant heat flux, that means Q double prime S is a constant, and we have seen for that specific case the Nusselt number turned out to be a constant. It has a specific value which is equal to 4.36. So, the Nusselt number based on the diameter of the tube has a constant value of 4.36 when we have flow, laminar flow, simultaneous flow and heat transfer inside a tube, where through the surface we are adding a constant heat to the system. So, even though the temperature will keep on changing, once the flow is fully stabilized, the shape of the profile, shape of the dimensionless temperature profile will not change anymore. And we also saw that this 4.36 Nusselt number to be equal to 4.36 is universally valid irrespective of whatever be the Reynolds number, as long as the Reynolds number is within the laminar flow range. It is independent of the liquid and so on. So, everything combined together, the Nusselt number for the case of laminar flow inside a tube whose walls are experiencing a constant heat flux will turn out to be a constant. The way we have done that, in order to do that, we need to know, we have defined what is the average temperature, the area average temperature, which we have denoted as Tm, the mean temperature of the fluid, which at a given axial location is a constant, since we have averaged it out across the flow area. So, this Tm, the heat transfer coefficient, is defined in terms of Tm, the Ts, the temperature of the surface, and Tm, temperature, the mean temperature of the fluid. The Nusselt, the heat transfer coefficient is defined by the Newton's law of cooling, which connects Q double prime S, which is the surface heat flux, to the difference in temperature between the wall, which is Ts, and Tm. Both Ts and Tm are functions of x for the case of constant heat flux. So, H is defined as heat flux Q double prime S divided by Ts minus Tm. So, this H, when we use it in terms of the Nusselt number, in last class we saw what its value H d by k is a constant and is equal to 4.36. So, we will not derive the other other type of flow where the surface is maintained at a constant temperature Ts. So, obviously, the flux will vary, but the temperature of the wall will remain a constant, and as I have told you in the previous class, this is a very common situation when we have condensation taking place on the outside. So, if we have steam condensing at a specific pressure on the outside of a tube, the temperature is going to remain a constant, and that is something which has many practical applications. So, therefore, the same type of analysis can also be done for the case of constant wall temperature, and we would see that we will not derive it, but similar to the case of constant heat flux, the Nusselt number for the constant surface temperature will also be a constant, and its numerical value would be equal to 3.66. So, therefore, it is again independent of the Reynolds number, it is independent of the type of fluid, and so on. So, to summarize, what we see over here, what we have done in the previous class is that for the case of laminar flow in circular tubes and for the case of constant surface heat flux, this Nusselt number turned out to be equal to 4.36, and this is also for the case of fully developed flow, thermally fully developed flow. Okay. So, this we have seen, and the only property K that appears in the Nusselt number relation, K is evaluated at Tm. So, whatever be the mean temperature of the fluid, the physical property, the thermophysical property K is evaluated at that condition, at that temperature. The second one, as I said, is a constant surface temperature case, and this is also the case of fully developed flow, thermally fully developed flow, and following the similar type of analysis which I will not do in this class, the Nusselt number based on the diameter of the tube turns out to be 3.66, and in this case Ts is a constant. So, that is the other relation which we have for the case of constant surface temperature. Ts is a constant, whereas in this case it is a heat flux, surface heat flux, which is a constant, and as before the K is evaluated at Tm, which is the mean temperature of the fluid. So, up to this point it is fine, but the problem comes is how do we expand these results, how do we extrapolate these results for the case of turbulent flow. Now, we understand that turbulent flow is much more complex than the laminar flow, because in turbulent flow there would be other means of transport of heat rather than simple convection and conduction, because in turbulent flow it is characterized by the formation of eddies, and those eddies are packets of fluid which carry more energy or more momentum when we have turbulent flow in such a case, and therefore the equation of energy takes up a much more complicated form. If you recall from your fluid mechanics, the Navier-Stokes equation, which is the equation of motion, will have additional terms which are collectively called as Reynolds stresses when you have turbulent flow present in the system. Similar to that, when you have turbulent flow and heat transfer, that heat transfer is taking place while the flow is in the turbulent regime, we will have additional terms, the heat transfer is going to be augmented by the presence of these eddies. So, it is difficult to express these results for turbulent flow, and therefore, an alternative approach must be taken. And the tool that we use, the tool that we are aware of already is the similarity, is the analogy between heat transfer and between momentum transfer. I have already taught you what is this analogy. We have the simplest possible case of Reynolds analogy, when Prandtl number is equal to 1. So, we could say that the Nusselt number and the friction coefficient they will become identical, or the Stanton number based on heat is going to be equal to Cf, where Cf is the friction coefficient times REL by 2, where REL is the Reynolds number. So, that analogy if we can use, and if we know what is going to be the expression of Cf or expression of F, the friction factor Cf or the fanning friction factor small f, if we know their relations in momentum transfer for the case of turbulent flow, then through the use of the analogy we can obtain an expression for Nusselt number in turbulent flow by the use of the analogy. That is the importance, that is the utility of the analogy, which lets you use expressions obtained in one type of transport process, for example, in this case the momentum transport process, and how do I correlate that with the heat transfer process that is taking place inside the tube. Now, what is the expression for F, the friction factor, the fanning friction factor? How do I obtain the value for the case of turbulent flow? All of you have studied fluid mechanics, and you know that the friction factor for turbulent flow is or can be evaluated through the use of the Moody's diagram. So, Moody's diagram gives you the value of F, the friction coefficient, as a function of Reynolds number even for the case of turbulent flow for smooth pipes as well as for rough pipes. So, you get a family of curves for different values of smoothness of the pipe or different values of roughness of the inner surface of the pipe, and therefore, at any given value of Reynolds number you should go to the curve corresponding to the roughness that your tube has and read what would be the value of F. That is what Moody's diagram is all about. So, if I can express this friction factor F as a function of Reynolds number, then it would be easier for me to extend this result for the case of heat transfer as well. So, for the turbulent flow inside a pipe, we have to use the analogy between heat transfer and momentum transfer, and knowing the expression of F from Moody diagram, I should be able to obtain an expression of Nusselt number. That is how we treat turbulent flow in a pipe, in a tube, when that flow is taking place in a tube and we are experiencing heat transfer in turbulent flow. So, without going into the analytical solution the way we have done for the case of laminar flow, we take the help of analogy to arrive at the expression for Nusselt number, and that is what I am going to show you over here. So, let us say we now concentrate on turbulent flow in a circular tube. In just to recapitulate what I have already shown you, the friction factor F from which you obtain from Moody diagram is related to the Reynolds number based on the diameter of the tube to the power minus 1 by 4 for RED, Reynolds number based on diameter greater than 2 into 10 to the power 4. This is the smooth pipe approximation, and I have also told you that the case for the case of turbulent flow, the flow conditions are affected less in the case of when you have roughness in the pipe. So, roughness in the pipe affects laminar flow more, and therefore, the transport coefficients, for example, F and so on, they will get affected more when you have the flow in the laminar condition as compared to the turbulent flow. So, the microscopic roughnesses which are present on the inside surface of the tube affect the value of F, the friction factor, more as compared to that in the turbulent flow. And for highly turbulent flow, since the boundary layer thickness is large as compared to laminar flow, these microscopic imperfections or roughnesses on the surface, they do not affect turbulent flow that much. So, the relation that I am using is for smooth pipe, but they can also be used for rough pipes as well. The friction factor, as I have shown in that correlation, is directly from the Modi diagram. So, the turbulent flow part of F as a function of Reynolds number for a smooth pipe is expressed by the function that I have written as F equals 0.184 Reynolds number to the power minus 1/4. Now comes the analogy part. The analogy tells us that Cf by 2, and by analogy here I am using Chiltern-Colburn analogy. The Chiltern-Colburn analogy essentially tells you that Cf by 2, where Cf is the friction coefficient, and if I do that with fanning friction factor, so the relation between Cf and F, as I have told you in the previous class, Cf is simply F by 4, it is due to definition only. So, Cf by 2 would be definitely then equal to F by 8, and the analogy tells me that this is going to be Stanton number into Prandtl to the power 2 by 3. That is what the Chiltern-Colburn analogy is all about. So, when I expand this Stanton number, it is going to be Nusselt number based on the diameter divided by Reynolds number based on the diameter times Prandtl number, and I have Prandtl number to the power 2 by 3. So, this is what is Stanton number. So, therefore, the F, the friction factor F, if I put from here from the correlation between F and Reynolds number from the Modi diagram, then what I have on this side is, this is going to be function of Reynolds number, and here I have Nusselt number, Reynolds number, and Prandtl to the power minus 1 by 3. So, utilizing the expression of F from here, I can write Nusselt number based on diameter as 0.023 Reynolds to the power 4 by 5 into Prandtl to the power 1 by 3. So, this is known as the Colburn equation. Okay. So, this Colburn equation simply gives you the expression for Nusselt number for when the flow is turbulent. It underscores, it highlights the importance, the utility of the analogy between heat transfer and momentum transfer, the Chiltern-Colburn analogy, which is valid over a wide range of Prandtl number as I have shown before. So, Chiltern-Colburn analogy lets me obtain an expression for H or Nusselt number in highly turbulent flow by simply using the expression for the fanning friction factor F obtained from the Modi diagram. So, the relation of F or empirical relation of F versus Reynolds number is substituted in the Chiltern-Colburn analogy to obtain an expression of Nusselt number for the case of turbulent flow, which is known as the Colburn equation, which says its Nusselt number is 0.023 Reynolds to the power 4 by 5 and Prandtl to the power 1 by 3. It has been shown experimentally that a slightly better result can be obtained if this constant 0.023 is changed somewhat, and therefore, another relation which is mostly shown in the textbook is known as the Dittus-Boelter equation, which is Nusselt number to the power d as 0.023 Reynolds to the power 4 by 5 but instead of Prandtl to the power 1 by 3, we have a constant which is n. So, this is the Dittus-Boelter equation, which is more commonly used for the case of heat transfer. Now, this n will have a value equal to 0.4 for heating, which is when the temperature of the surface is greater than the temperature mean temperature of the fluid, and n is going to be equal to 0.3 for cooling, when Ts is going to be less than Tm. And the applicable limit of Prandtl number is quite large, 0.7, which is the standard Prandtl number for the case of air, and this, so it is a large variation in Prandtl number, and Reynolds number is more than 10,000. So, and L by D is greater than equal to 10. So, L by D greater than 10 tells you that it is a thermally fully developed flow. The Reynolds number greater than 10 to the power 5, 10 to the power 4 tells you that it is in the highly turbulent region, and the range of Prandtl number ensures that this relation can be used for a wide range of liquids, from air on the one hand, and for a high value Prandtl number liquid, that this same equation can be used with only one consideration. I mean, in Colburn equation the Prandtl number coefficient is fixed, but n takes a value equal to 0.4 for the case of heating, whereas for cooling it is 0.3. So, for all future calculations we will stick to Dittus-Boelter equation, which is again just an approximation added to, or an empiricism added to Colburn equation to take into account whether it is a case of heating or whether it is a case of cooling. Now, if you recall, I said that the Tm, the temperature, the mean temperature is used to calculate the physical properties. Now, when a fluid is flowing through a tube, the temperature will keep on changing, and as the temperature will keep on changing, if it is a case of heating, then the temperature will keep on increasing. So, the value of the thermophysical property will have different values at different temperatures. So, if the temperature change is not significant, then the values of K, thermal conductivity, that you evaluate will not be substantially different between the entry and the exit. K is not a very strong function of temperature, but there is one property of the fluid which is a strong function of temperature, and obviously the property which changes drastically, rapidly, significantly with a change in temperature is the viscosity. So, when you calculate the Reynolds number, what is the viscosity that you are going to use? Is it the entry point viscosity, and the Reynolds number is calculated based on that, or is it somewhere down the line where the temperature is more, the viscosity is less for a liquid, and therefore the Reynolds number will have a different value. So, whenever you are using a correlation in order to obtain the value of the Nusselt number, in order to calculate the Reynolds number, you must be careful about the temperature change that you expect between the entry and the exit, or some point in between. So, if I have to add a correction factor to take into account the variation of property, and the property in question would obviously be viscosity, because viscosity is the one which changes significantly between 2 points, then to this Dittus-Boelter equation a correction term for viscosity must be added. So, the next correlation that I am going to show you, its genesis for this correlation is to take into account the variation in thermophysical property, the relevant thermophysical property, which is viscosity. So, a viscosity correction factor is added to the Dittus-Boelter equation in order to enable, or in order to extend its applicability over a wide range of temperature change. So, that equation is known as Sieder-Tate equation. So, whenever you expect significant changes in temperature along the length of the tube, do not use Dittus-Boelter equation, but rather use Sieder-Tate equation that has a viscosity correction factor, empirical factor embedded to it. Okay. So, let us see what this looks like. So, when you have a large property variation, the equation to be used is Sieder-Tate equation. And the Sieder-Tate equation, this Nusselt number based on diameter is 0.027, the Reynolds number, the exponent remains the same, the Prandtl number remains the same, except a mu by mu s to the power 0.14. This additional term is added so as to take into account the possible significant variation of viscosity when the flow is taking place. So, this again has an applicable limit of Prandtl number between 0.7 and 160. The Reynolds number has to be greater than equal to 10 to the 10,000 and L by D is greater than 10. So, properties except mu s are evaluated at Tm. And as I said, it's the other properties are not a strong function of Tm. So, therefore, the property to be careful about is the viscosity, and mu s is the mu s is evaluated at the temperature. Another point which I must mention, that this correlation is valid for both for uniform Ts or constant Q double prime S. So, uniform Ts, uniform surface temperature or constant heat flux, this correlation is valid in both cases. Now, when I say correlation is valid, whenever you use a correlation, you have to keep in mind that this is not an analytic expression, it is a correlation. So, there will be some error associated with it, but you should always judge a correlation with the ease of its use and how much of error it introduces in your final calculation. So, the success of a correlation is judged by the ease of its use and the errors that it introduces into your overall calculation. So, judging by these two criteria, Sieder-Tate expression has proved to be a very successful relation to connect the Nusselt number for flow inside a tube, both for constant surface temperature and constant heat flux conditions for a wide variety of liquids and over a wide range of temperature. So, if your temperature of the wall is at 150 and the mean temperature is of the liquid is 30. So, you can have a significant variation of viscosity near the wall as compared to the rest of the fluid, and the correlation of choice is Sieder-Tate. So, we should, if there is a substantial temperature change, we do not use Dittus-Boelter, but we use the Sieder-Tate relation. There is one more complication. In many of the cases, many of the practical application cases, you not only have a circular tube, in some cases you have tubes, you have conduits through which the flow is taking place and it is not, the cross section is not circular. So, what do I do for the case of diameter when we have flow through a non-circular conduit? Can I still use the relations, the correlations that I have presented so far? Yes, we can, but we have to be careful to use not just a diameter, because there is no diameter, it's the flow is taking place through a thin duct. So, what is the diameter in such a case? So, the diameter to be used for non-circular conduits is the hydraulic diameter. So, always use hydraulic diameter to calculate what is the Nusselt number, and then use either the Sieder-Tate or the Dittus-Boelter equation. So, the non-circular nature of the conduit is accounted for through the introduction of the hydraulic diameter. Please keep that in mind when you are making a calculation for heat transfer in non-circular conduits. So, I am going to write that over here. So, if it is a non-circular tube, the hydraulic diameter, which is defined as 4 AC by P, this you must know from your fluid mechanics, which this AC is the cross sectional area and P being the perimeter. This hydraulic diameter is used to calculate what is Nusselt number, what is the Reynolds number based on the diameter. So, the Reynolds number that you calculate over here is to be, for the non-circular case, is to be substituted by the hydraulic diameter. Now, one thing I would also like to bring to your notice in the case of Sieder-Tate equation or Dittus-Boelter equation, that this L by D is taken to be greater than 10. That means the flow is fully developed, but there would be situations in which the length of the pipe is such that the entrance region is not insignificant. So, there is a significant section of the pipe in which the flow is still developing. So, the correlations which we have obtained for fully developed flow, namely the Dittus-Boelter equation or the Sieder-Tate equation, is not valid when we have significant portion of the pipe under the developing flow condition. So, if you want to have a generalized relation which is valid for turbulent flow, which also takes into account the developing part of the flow, a correlation which takes into account the significant difference in temperature between the tube wall and the mean temperature. So, that relation I am going to write next, which can be used over a wide range. So, when I consider entry region, that means the region where the flow is still developing, the relation to be used is Nusselt number based on diameter, and here I say it is the average Nusselt number is 1.86 Reynolds Prandtl L by D to the power 1/3 and a viscosity correction factor as before, mu by mu s to the power 0.14. So, the key word here is when I consider the entry region. This expression is purely empirical. So, from an empirical, that means over a large number of experimental results, when they are expressed in the form of a correlation, it turns out to be this. So, what I have shown you in this class is that the Nusselt number for laminar flow when the temperature of the wall is constant is again it is a constant and its numerical value is equal to 3.66, like what we have for the constant surface heat flux where the value was 4 point something 4.6. But the problem comes when we try to extend our analysis for the case of turbulent flow, which as I have said is not possible from first principles, since the equation of energy is very complicated because of the presence of those eddy terms, and we do not know how to account for it and how to obtain an analytic solution as we have done for the case of laminar flow. So, the method of choice is the use of analogy, and we are going to we have used the modified Reynolds or the Chiltern Colburn analogy and used the use the expression of F, the friction factor from Moody diagram, and what we saw is that Cf by 2 is equal to F by 8, and we have the Stanton number times the Prandtl number to the power something, and we obtain an expression of the Nusselt number as a function of Reynolds number and Prandtl number. This expression, when we extend it, when we take into account the property variations as well, gives rise to Sieder-Tate equation. So, for most of the practical problems, we will either use Dittus-Boelter equation when the temperature change is not significant, or Sieder-Tate equation when the temperature change is significant. But both of these equations assume fully developed flow. When we have to consider developing region as well, the last equation which I have shown, which is this equation, the last equation that I have shown is to be used when I consider the entry region as well, so that the entry region is comparable in size to that of the overall length of the pipe. So, therefore, this will conclude our treatment of internal flow and heat transfer when the flow takes place in a pipe. That pipe could be circular in cross section, it could be non-circular as well, in which case I have to use hydraulic diameter. So, what I am going to do in the coming 2 classes is solve a few problems, so as to show you how the concepts that we have discussed so far can be applied in real situations. When a flow is taking place in a tube or in a pipe, how to calculate the heat transfer coefficient at the inside of the tube. We know how to calculate the heat transfer coefficient on the outside of the tube, and there are several other situations that I need to discuss which tells you about what is the heat transfer coefficient when you have, instead of one tube, you have a bank of tubes and you have some flow or some condensation is taking place, which would give me the value of HO, that is the convective heat transfer coefficient on the outside of the tube. But for the past 3 classes, I am considering the internal flow. So, I know how to calculate HI in laminar flow, in turbulent flow where the property variations are significant, and in turbulent flow where the length, the entry length is not insignificant as compared to the overall length. So, our next 2 classes we are going to solve problems on internal flow.